Okay, so this is a re-recording of the audio used for the lecture for SM1 and MM1 for week 12. We're talking about Introduction to Linear Equations. As you can see here, we're talking about three main things: reflection, dilation, and vertical translation. It's really important that you understand these three words in depth because we're going to apply them to all the functions that we use throughout the rest of the year. The first one here is about a reflection. A reflection in this case typically means a reflection on the x-axis, and it is to do with the negative idea of a function. So if you imagine your y equals x function, which has a positive gradient like this, and y equals minus x is reflected on the x-axis and has a negative gradient like this. It turns the positive quadratic, this shape, into a negative quadratic, which is this shape. The concept of a dilation. So dilation I talked about as a reference to your eyes, for example. When a light shined in your eyes dilate so that, or contract or dilate. So it's about dilation from the x-axis, which is a distance. So basically with linear functions, all we're talking about here is getting steeper. In our HK forms that we talked about last week, there was A, H and K, and A is the measure of the dilation. If it's more than 1, it's getting more steep. If it's less than 1, it's getting less steep, so more flat. And then this idea of a vertical translation, when we move things up or down on the y-axis. So we talk about then different ways of sketching functions. We're looking at this particular function having a standard form y equals mx plus b. Just zoomed out a bit so I can fit the whole thing onto a page. Here we go. Okay, so we're looking at this particular function and I'm going to step through how to sketch that. So we're looking at the three ideas around reflection, dilation and transformation. There's no reflection here, there's no negative. There is a dilation by a factor of 2. This is our dilation here, our steepness. How steep is the graph? It's more than 1, so it's getting more steep. And this here is actually our y-intercept. That's what the b in this particular form means, is our y-intercept. So then we just begin thinking about how we can map that out onto our Cartesian plane. Start with y equals x. 2x is steeper, moved up 4. X, 2x plus 4, move it up, sketch it in. And we know that's moved up 4, we're marking the point 4. That is in itself a sketch, that's all that's necessary. A sketch is really important. It gives us an idea of indication of direction, shape, form. We can also add in here some more information that would help us get an idea of how steep this is. We add more information here, we turn it into a bit of a graph. We want to find the x-intercept. The x-intercept happens when y is 0. So we substitute y as in 0 here. You should be able to do this in your head. We rearrange the equation. So when y is 0, minus 4 divided by 2 is minus 2. So then very quickly we step through these other functions. We're looking at y equals minus 3x minus 7. So we should be able to picture what that looks like. And you should get something like this. Of course we could turn that into a graph by finding the y-intercept. And we rearrange this equation. Take the 7 over, divide by minus 3, we get minus 7/3. Again, we're looking at these three things, always reflection, dilation, vertical translation. Okay, now we're looking at a different one here. Same as before, so we look first. Is there a reflection? No. Is there a dilation? It's less steep, and then it's moved down 1,000. Should be able to sketch that straight in. Of course, if we want to add in this x-intercept here, we rearrange the equation. And we find out that this point here, 1,000 divided by half is 2,000. Okay, do a few more. Just a decimal, we look at firstly reflection, yes, so now I know I'm going to have a negative gradient. 0.78 is less than 1, so it's going to be flatter, and it's moved down minus 0.6. So we should be able to draw that in now. If we want this y-intercept, we rearrange it, we get 0.6 divided by minus 0.78. And we work out what that is as a decimal and write it in. And this one here, looking at some large numbers again. Firstly, look for a reflection, there isn't one. Dilation, yes, by a factor of 1,000, so very steep. And move down minus 267. We get something that looks a little bit like this. Here we have our x-intercept, just 267 thousandths, so very tiny. Just going to look at some special ones here. So we've got y equals 4, and then there's no x, so that means we've got a horizontal line. Y is always 4, doesn't matter what x is. In this case, the gradient of a horizontal line is 0. It's like we had 0x here on the end. Here we have a x equals minus 2. This means x is always minus 2, doesn't matter what y is. We end up with a vertical line. And we say in this case that the gradient is undefined. It's not infinite, it's not 0, not defined. Moving on to now to sketching functions that are of this form. Ax plus by equals c. Now in this case we don't have instantly the gradient, we don't have instantly particular intercepts, but what we can work out very quickly are the x and y intercepts. So the x-intercept happens when y is 0, so basically that disappears. When y is 0, we can then see that 2x is 6, so we can see that x is 3. Mark that in. Y-intercept happens when x is 0, so basically that doesn't exist. We get 3y is 6, and we can see there that y is 2. We've got 2 points, basically then we just draw in a dot to dot. Let's try another. X plus y is 7, so the x-intercept happens when y is 0, so we cover that up. We can see that x is 7. And then the y-intercept happens when x is 0, so we cover that up. We can see that y is 7, and we draw that in. Next one here, you can see here that x is 10 quarters, 2.5. And when y, we get minus 5. Dot to dot. We talked a little bit about gradients, and there are 3 important points to notice here. So we've got the gradient is basically the rise over the run. Another way to think about it is for every step across, and we read from left to right, so it's every step to the right. How far up or down have you gone? If you're going up, the gradient's positive. If you're going down, the gradient's negative. In this case, we go across 7, we went down 7. Rise over run, minus 7 over 7. It's minus 1. In this case, we go across 2.5, so every 2.5 steps across, we go up 5. So even though there's negative 5 here, where the rise is actually we're going up 5, so it's positive. Positive gradient, as you can see, this way. The other idea about gradients is we could use 2 points, x2, y2, and x1, y1, and using our Cartesian plane we can see that the rise is the difference in the y coordinates and the run is the difference in the x, so there's just a rule that can help us with that. So you can either turn it into a right angled triangle, measure off the distances yourself, or use this particular rule. Now there are 2 important rules that we need to know around how to, that we could use to help us get an equation from a graph or from information given. The first one is called gradient intercept form. Here we have the gradient, here we have the intercept. If you know those 2 things, put it into this equation and get your rule. The other one is called the point gradient formula, where we have a point here, x1, y1, and the gradient m. Put it in, rearrange, get your equation. Then we had a quick look about how to get the equations from these particular forms. This first question, we could use either point gradient. We could work out the gradient and the point, or we could use gradient intercept. So the first one we use is our point gradient. We decide to use this point or this point. It doesn't matter. We could use 0, 3 or minus 1, 0. And that will be our x1, y1. We also need to know our gradient, which is rise over run. So for every one step across, I go up 3. So my gradient is 3. Put it in here. I can choose either point. I decide to use this one because there's a 0y. And my gradient is 3. So it's 3x plus 3. That's using the point gradient formula. I could also use the gradient intercept method. I'd just need the gradient, which I've worked out in this particular part. And I know the intercept is 3 because I can read that off the graph. So once I've got those two pieces of information, I plug it straight in, 3x plus 3. So the next one we're left with 2 points. So we don't have the y-intercept that we could read off easily. So we decide that we're going to find the gradient first, y2 minus y1 over x2 minus x1, or we can turn it into a right-angled triangle here, read the distances straight off. This is my preferred method. Of course, if you like the rule, you can use that. I see that I have to go from minus 4 to 8. That's a distance of 12. And I'm going from 2 to 4, which is a vertical distance of 2. So rise is 2 and run is 12. My gradient is 1/6. Now I just use my point gradient rule. Can use either of these points as x1, y1, 8, 4 or minus 4, 2. I tend to use the one with the least amount of negatives. Of course it will work for either point, it doesn't really matter. Plug in my gradient as 1/6. And then I'm just left to rearrange that and make it tidier. So the very last example here, I can use my point gradient. My intercept here is 4. And my gradient, don't know, so I need to work out my rise and my run. So for every 12 steps across, I go down 4, so it's minus 4/12, which is minus a third. That's my gradient.